All right. So what the heck is going on with this problem, guys? If we graph this function, and hold on, we don't need me to graph it, right? Don't take my word. Don't take my word for it. Let's graph this. So if we graph this, it's h equals 16 cosine of 1 divided by 500 times d. All right, we'll use x's and y's. And oh, it didn't matter. So essentially, what we care about, right? We care about the year. So the x is going from 0 to 360. So 365 days in a year. Okay. And let's say we're, oh wait, I think I see what's going on maybe. Let's say y goes from like 0 to 20. Interesting. So this is what this plot is. This is a garbage graph though. How is this not this makes no sense. This says on the 0th day of the year. On the 0th day of the year, there's 16 hours of sunlight. January 1st, 16 hours of sunlight. Are we in the southern hemisphere? December 31st is way less sunlight. And then you get like overnight 8 extra hours of sunlight. Is it actually in degrees? No, it's definitely not in degrees. I didn't think it was in degrees. Degree graph, definitely wrong. What's going on here? No, it should be sinusoidal. And it should have a period of 365 days, right? So you'd expect the shortest day of the year to be, in December at the winter solstice. And then it's going to go up until the longest day of the year, which is summer solstice, and then go back down. So it should look like this. The period's all wrong, though. Period should be 365. So I feel like, here, hold on. Oops. I feel like it should look something like this, where we sit at 12. And then, like, let's say, this is what I feel like it should look like. Or like in January, maybe you have like 6 hours of sunlight. And it's over here. There needs to be a slight phase shift for winter solstice. It's in the middle of December, not the end of December. I feel like it should look something like this. Let's add a phase shift. Let's move it left just a little bit. So like plus 0 point. Yeah, it should look something like this. For the day, for the sunlight, the hours of sunlight on a certain day. So is the book just full of garbage, or is the book full of garbage, or are we fundamentally misunderstanding the problem? It's this problem. Here's an idea. I think we have an incorrect assumption, and I think the problem is not specific. Because our answer, 13 hours and 46 minutes, makes sense for September 24th. What I think could be it, and yeah, that's probably the explanation, Jarud. What I think is going on, actually, and I can email the publishers, they'll probably fix this, is this function is probably not modeling the entire year. The entire year would look something like this. This might just be a local function. Maybe this function is really only modeling it for like September, a single month or something. And then I could buy it. So whenever you do a math model, you have to specify what domain is this model accurate for. And so maybe that's what they're going for. That's the only rationalization I can think of. Otherwise, this is completely garbage. And same thing with this one, right? These are essentially very similar functions. Although this one is very similar, but it's modeling in February. You plug this into February, you're gonna have a really long February. But again, maybe it's in the southern hemisphere. This is bizarre. Yeah, if it were just for 1 month, right? Wouldn't they redefine D? Who makes a function and say this is valid for the domain like 200 to 230? That's kind of weird, right? Why not just say, you know, where D is the dth day of September? Then you don't have to figure out that it's 267. I think this is just a garbage example. I should talk to someone else about this. But the problem with talking, so the natural people I'd talk to this about are the other math professors at the college. But the problem is I'm really trying to push the department towards using free textbooks. And if I show them this free textbook and say, hey, look at this garbage example in this free textbook, it's going to work against me. Ah, man, this is I don't think I can be missing something. I think this has just got to be garbage. My best explanation, my best guess is just that it's a local, it's only valid locally. I don't like that answer. Maybe I'll pull a fast one on my face-to-face class tomorrow and give them this function instead. There are bad problems in every textbook, yeah. But just because you know something logically doesn't mean it doesn't affect the way that you feel. And it would still probably, yeah. Yeah, maybe here. Hold on. I'm talking about this with my face-to-face class tomorrow. Let's say h equals -6 cosine of 2 pi over 365 x plus 0.1 plus 12. Great. They'll never know. We did it. We did it, guys. Twitch chat saves the day. Because this looks like a much better function. Fun fact, my last job was doing slot machines and creating math models for slot machines. So this sort of thing was kind of my job. It was a lot more probability and a lot less like sciencey. But creating functions and stuff that models reality. So this is much better. Much better. Again, plus 12 is not, or plus 0.1 is not actually ideal. It would need to be like 0.15 or something. All right. So winter solstice is like around the 15th or something. But anyway, it's just a model. It doesn't mean to be a perfect model. Anyway, that's kind of funny. I'm going to have to show somebody though, some other math, like really math person. Oh, it's December 21st? Yeah, I don't know. Well, then this is pretty close to 0.17. Yeah, you're right, Jared. You're right. But it doesn't mean it doesn't bother me. Yeah, probably nobody would notice. Oh, man. You know what I should do? When my other trig class gets to like graphs of functions, and we talk about like period and amplitude and phase shifts and vertical translations and stuff, I should tell them this problem. I should tell them about this and have them talk about it. That would be fun to do. I might just do it like before class so we don't spend any actual class time on it, but get some good mathematical discussion once we've covered those topics. I think that'd be a good idea. That'd be fun. Anyway, does anyone have any questions? Somebody had a calculus question earlier. If you're still here, who was it? A Blair boy. If you want to ask that calculus question, if you're still here, I'll do it. Or if you're not, then I'll probably be done. Oh, you are here. Yeah. So you're looking at this limit, right? All right, guys, this is now a calculus stream. Audible. This is perfect because I didn't want to waste this piece of paper. So I think the question was, what is the limit as x goes to 1? of x to the 4th minus 1 divided by x to the 6th minus 1. Also, Blair Boy, if you do want to ask questions on calculus, feel free to ask. I will wait to the end of my lecture, but I like to ask for questions. But I'm more than willing to do them. I'm not going to spend like 3 hours doing like 50 problems, but you know, question here is good. Yeah, that's exactly it. You factor it. So there's a very common factoring formula that may not be obvious why we use it here. Good catch, by the way, Starboy. We use this, except it's x to the 4th. So we have an x squared minus 1 and an x squared plus 1. And the denominator is x cubed minus 1, x cubed plus 1. Yeah, and then, wait, is this even necessary? Wait, maybe this is necessary. Yeah, it's probably necessary. That's one way to do it. Another way of doing it is using L'Hopital's rule. I would just use L'Hopital's rule. I hate factoring. I don't know if you've covered L'Hopital's rule yet, though. But yeah, you could keep factoring it here if you haven't done L'Hopital's. So this is going to be x minus 1, x plus 1. And then x squared plus 1 is prime. But we don't care about x squared plus 1 because that's not causing any zeros anyway. And the bottom, factoring perfect cubes is a different formula, but you can find it. It's x minus 1 times x squared plus x plus 1. Then we have x cubed plus 1. Okay, you haven't talked about L'Hopital's. Yeah, L'Hopital's says that if you have 0 over 0 on a limit, you can take the derivative of the top and the derivative of the bottom. And that limit will be the same. So you'd have 4x cubed divided by 6x to the 5th. And just cancel. And then when you, here, we'll do it both ways. We'll give you a sneak peek into the future of your calculus. So these cancel, right? Now everything is just ones. So, oops, I dropped my limits, guys. Don't do this. If you do this in a calculus class, your calculus professor will be very grumpy. Don't lose your limits. All right. So now, well, now we don't need the limit. We can just evaluate the limit. Okay. So it's going to be 1 plus 1 is 2. 1 plus 1 is 2. 1 plus 1 plus 1 is 3. 1 plus 1 is 2. We get 2/3 that way. But yeah, essentially L'Hopital's rule says that if you have 0 over 0 in a limit, we use quotes to show a 0 over 0 case. What we can do is take the derivative of the top, which is just 4x cubed. Oh yeah, you probably haven't even started talking about derivatives yet, maybe. And the derivative of the bottom, which is 6x to the 5th. Well, now x cubed cancels with this. It takes away 3 of them. So we have 4 over 6x squared. And again, now we can plug in 1 no problem. We get 4 over 6 times 1 squared. But again, 1 squared is just 1. It's just 4/6 or 2/3. Okay. Yeah, you'll probably start with the definition of the derivative, which is a little tedious. But eventually you get a lot of nice shortcuts to make derivatives easier. And then derivatives, in turn, can make limits easier. L'Hopital's rule is a really weird proof too. I don't even remember it. It's hard though. It's usually not covered in a calculus class. We differentiated cooldown. Any other questions by anyone? Otherwise, I'm going to be logging off soon. But I like talking about math. We'll see how long this channel survives. It really is so much easier. But that's true with a lot of math, right? If you know the harder math, you can make the easier math so much easier than what it used to be. Like the definition of the derivative is a case of that, right? So if you look at the derivative of x to the n, there's a rule called the power rule that says the derivative of x to the n is just n times x to the n minus 1, where you just bring the power down as a coefficient and then subtract 1 from the exponent. And sure, once you know the power rule, that's super easy. But in order to get the power rule, you have to know what a derivative is. And this actual derivative, by definition, is the limit as h goes to 0 of x plus h to the n minus x to the n over h. And this limit is not trivial to this is not a trivial calculation. And this is actually the proof of where the power rule comes from. You have to use, I think, the binomial theorem To get this, hold on, we're doing this now, all right? We're doing this. I think it's called the binomial theorem. And I think I know what the binomial theorem says. We use a summation here. Yeah, here it is. So we do use the binomial theorem here. Yeah, we've gone from trigonometry to Calc 1 to very difficult Calc 1. So binomial theorem says that this binomial being raised to the nth power is the sum from k goes to 0. You probably haven't learned about summation notation yet, but the sum from k equals 0 to, I think, n, right? Let me double check. Yeah, to n of n choose k, and you want to remember combinations from probability? N choose k times x to the n minus k times h to the k. Oh, we don't have enough room to write this. All right, and we still have a minus x to the n. And now you might say, hold on, we need to rewrite this. We need to rewrite this. What do we have? We have the limit as h goes to 0 of the sum, k goes from 0 to n, of n choose k, x to the n, x to the n minus k, h to the k, right? Yeah. And then again, we still have that minus x to the n over here as well, all over h. And you might say, this looks terrible. And it does. I don't remember this proof. I think this is how the proof went. Again, eventually we want to rewrite things and simplify things enough that we can just plug in h equals 0, which we can't do that yet. All right, well, what happened next? Oh, I know what happens next. Check this out. So in a summation, let's just take out the first one. This just means that we're adding up n plus 1 of these. And the first one is just this thing when k is 0. The second one is when k is 1, etc. So let's just take out the first one. All right. So if we take out the first one, that's when k equals 0. So the first one says n choose 0 times x to the n minus 0 is just x to the n. Oh, this is beautiful. This is beautiful. You guys are going to get so happy. Oh, it's been too long since I've done calculus. And then h to the k. And again, k is 0 for the first term. So this is just the first term in the summation. There are n more of these. Okay? So we're not going to write all of them. So now we already took out the 0th term. So now we're only left with 1 to n of the same thing, n choose k, x to the n minus k times h to the k. And we still have the minus x to the n over here. We're getting a little long over here. It's fine. Because now something huge happens. So if you don't remember your combination formula, that's fine. But n choose 0, it doesn't matter what n is. N choose 0, this is just 1. H to the 0, that's also 1. So what is this first term here? This first term is just an x to the n. And you know what that means? That means we have x to the n minus x to the n. These two things completely cancel each other out. So what are we left with? The limit as h goes to 0 of the sum, k goes from 1 to n, of n choose k, x to the n minus k times h to the k over h. And here's the big punchline. That was one of the big punchlines. This is a joke that it's just a great joke. It has multiple punchlines and they're all hilarious. Okay? Is now every single term in the numerator has an h. Right? The very lowest h is when k is 1, and then there's only one h. The very last one is when k is n, and there's n h's. So if you wanted to, and this is probably a good intermediate step, you don't have to do this, but if you wanted to, you could factor out an h from the summation. This is just a bunch of things added all together, and they have an h. We're factoring out an h from all of them. So we have an h in front, sum k equals 1 to n. Here it comes, guys. N over k, sorry, n choose k, x to the n minus k, and we lost an h. So it's not h to the k, it's going to be h to the k minus 1. Because again, if you multiplied h times h to the k minus 1, you add the exponents, you add 1 to this, and you just get k all over h. And because we have h times something over h, the h's are going to cancel. And now that we don't have an h in the denominator, we can evaluate the limit by just plugging in the number. So if we plug in h equals 0, what do we get? We get the sum, k equals 1 to n, of n choose k. Again, I've not done this before. Or I have done this before. It's been a while. I don't know where this is going, but I'm pretty sure we're on the right track. N choose k, x to the n minus k, times h is now evaluated to be 0. Whoa! Uh-oh. You might think we made a mistake. We're taking the derivative of this monomial, and we have it multiplied by 0. Multiplied by 0 means that it's going to all zero out. But not everything's a 0 here. Okay? Also, we goofed. We honestly goofed. I said I haven't done this proof for a while, right? We should have done one step before plugging this in. Because, right, if we look at when k equals 1, that's the term that we need. To determine when k equals 1, this has an exponent of 0. So we plugged in 0 a little too early. We do not want 0 divided by 0. So let's wait on that, okay? Let's factor out, or let's take out another term. Let's take out the first term of the summation. And the first term of the summation is when k equals 1. So let's take that out. When k equals 1, we have n choose 1. N choose 1 times x to the n minus 1. Oh, this is looking familiar. Times h to the 1 minus 1. And then again, we have all the other ones. Sum from k equals 2 now, because we took out the first one, to n of n choose k, x to the n minus k, h to the k minus 1. Ah, there we go. This is good. Because now everything in here has an h. So when h equals 0, all of this goes to 0. This is the combination formula. It has to do with, like, if you have a bunch of marbles in a bag, how many different combinations could you grab out? So if I have 5 marbles in a bag and I'm choosing 2 and they're all different colors, 5 choose 2, and it essentially means the formula for n choose k, side note, is n factorial divided by k factorial, n minus k factorial. That's what combination means. It might differ depending on the country, I don't know. So anyway, this limit goes to 0. This limit we can just plug in, right? H to the 0, that's 1. In fact, there's no h's here at all. What are we left with? N choose 1 times x to the n minus 1. But n choose 1, if you use this formula, is just n. Whoa! Okay? I told you it was that. That's a super easy formula. And the super easy formula comes from the definition of the derivative. This is what a derivative means. So we use the definition of the derivative on that function, use the binomial theorem to simplify, did a couple other nice tricks with summation, and that's where the formula comes from. Just some good old-fashioned calculus. All right? And that's the whole point of a lot of things in math. That's where formulas come from, is essentially we do something really hard so that we never have to do it again. All right, everyone knows the quadratic formula, right? X equals negative b plus or minus the square root b squared minus 4ac. Do you know where the quadratic formula comes from? It comes from blood, sweat, and tears of mathematicians. Quadratic formula can be used to solve quadratic equations of this form. We have to complete the square of this generic polynomial to get the quadratic formula. That's where it comes from. Quadratic formula is nice and easy, but it comes from a method that people hate, completing the square on a completely general problem. So real quick, before I end off, I gotta go to bed. I gotta get off sometime tonight. If you use a complete the square, you have to have your coefficient of x squared be 1. So we have to divide everything by a. 0 divided by a is still going to be 0. And now we have to add half of the middle term squared to both sides. And we have to move the c over a over. So half of the middle term squared is b over 2a squared. And we move the negative c over a over. And we added, again, b over 2a squared. Let's write that as b squared over 4a squared. And now on the left-hand side, we have a perfect square. That happens every time you complete the square. And we get x plus b over 2a squared. On the right-hand side, we need a common denominator. So we have b squared over 4a squared minus, we need to multiply this by a over a. ac over a squared. This should be looking familiar pretty soon. Okay. And now we have to square root both sides. X plus b over 2a equals plus or minus. Remember, when you square root both sides, you need the plus or minus. Combine, oh, crap. We didn't need to multiply by a. We need to multiply by 4a. B squared minus 4ac over 4a squared. Subtract the b over 2a over. You get negative b over 2a plus or minus the square root of b squared minus 4ac. The denominator, though, is a perfect square. We can write that as 2 times the absolute value of a. The square root of a squared is absolute value of a. We need absolute values here. But the reason we can drop them is it doesn't matter whether a is positive or negative. Because we have the plus or minus, we already take care of both. So we can drop the absolute values here. And now they have the common denominator, so we can combine the fractions, negative b plus or minus the square root of b squared minus 4ac, all over 2a, and that's where the quadratic formula comes from. This looks like garbage. Nobody wants to do this. So some mathematician, some caring, selfless mathematician put blood, sweat, and tears into completing the square like this so you don't have to. And you can just use the quadratic formula. You can implement the quadratic formula algorithm into a computer or a calculator and just plug in A, B, and C and get the right answer. So many formulas come from this. We just see, all right, can I do this for a general equation? X to the n. This is as general as it gets for a monomial. Have to prove it with the definition. And it's not just have to prove it. It's like, well, how did you even know that this was this in the first place? Over here, quadratic formula. We just solved using complete the square for every polynomial. Every quadratic looks like this for some value of a, b, and c. Or every quadratic equation. So that's interesting. That is interesting. Anyway, that's enough math for me. This is a very sidetracked math session, but I had fun. Hope you guys had fun. Hope you guys learned at least something. At the very least, maybe you enjoyed yourself. There's a fun proof, though. I haven't done this one for a while. I was pretty sure I knew what to do. And I only made one mistake. I only made one mistake where we got 0 to the 0th power. That's no good. Anyway, every Tuesday, Thursday, and Wednesday at 8 o'clock Mountain Time, we're going to be back doing more trigonometry. All right? So if you like trigonometry, great, come. If you have other math questions, you can ask them after the trig lecture. Anyway, have a good night, everyone. I will be back not until next Tuesday, unless you know my alter ego, in which case I might be back tomorrow, and we'll be back Saturday for sure. All right, have a good night.